Bright Tuty. Every student matters.
Hello students, I am Shavika and we are continuing with the chapter Periodic Classification of Elements. So after we have understood the trend in which the way in which the classification works, let's move on to some trends and see how is it that different things go forth in the modern periodic classification. So the first trend that we will study is of valency. Now what is valency? Valency is the number of electrons an element will either take or give to achieve a stable configuration. So when we move from left to right in a period, as I've already explained this period to you, you will see that the number of valence electrons is increasing, but valency would first increase and then it would decrease. Let me show you how. So that is the configuration that I've written for all the elements based on their atomic number. I know that the K shell only has 2 electrons and then I put the remaining electrons in the second shell, and after 8 it gets filled, but the last element we have here has 8 electrons, which is a stable noble gas, neon. Now you see that the valency is the number of electrons it would give and take. So up until here the valency is increasing. The valency here was +1, then it became +2, then it became +3. But after here, the valency starts decreasing because now the valency has become negative. So because it has 5 electrons and it will take 3 more electrons. So here it's -3, here it's -2, and here it's -1. Here it's 0 because it's a stable configuration. But you see that the valency first increases and then it decreases. That is because the number of valence electrons, although are constantly increasing, first we have metals which are electropositive, and then we have electronegative elements which would rather take an electron rather than give away electron. So these would lose electron, whereas these would gain electron. Now when we talk about going down the group, what happens to the valency? So let's take the group 1. We have hydrogen at the top, which has just simply 1 electron. We have lithium, we have sodium, we have potassium. Now the valency you see here is 1, 1, 1, 1. So they all will lose 1 electron to gain a stable configuration. They all in fact have form cations and they all have the same valency. So no matter what group you're talking about, when you go down the group, the valency remains same. For a period, it first increases and then decreases. So that is about valency. When you go from left to right in a period, the valency increases then decreases. When we talk about the valency down the group remains same because the number of electrons in the outermost shell is same. The second property, the second trend that we will talk about is atomic size. Now what is atomic size? Atomic size is the radius of an atom. How do we measure it? We measure it by measuring the distance between the nucleus and the outermost shell. So the radius of the atom, which is the distance between the nucleus and the outermost shell, is called as the atomic size. We have an example of hydrogen given here. So the atomic radius of hydrogen is 37 picometers. Picometer is 10 to the power -12 meter. So you understand that what is atomic size? It is the distance between the nucleus and the outermost shell. It tells basically how big an atom is. Now, what is the trend when we move from left to right in the period? When we move from left to right, the atomic size decreases. Now, why does the atomic size decrease when we move from left to right? It is simply because the number of protons in the nucleus increase, and they exert a greater pull on the electrons in the outermost shell, and that is why the atom shrinks. So as the number of protons increase, there is an increase in the nuclear charge, because of which the electrons get pulled closer and the atom shrinks. We also have a case given here. So we have all these elements. We have boron, beryllium, oxygen, nitrogen, lithium, and carbon. We are asked to arrange them based on their atomic radius. So when you arrange them based on their atomic radius, you will see that the biggest is lithium, right? So I'm putting lithium first, it's the biggest. After that, we have beryllium. After beryllium, we have boron. After boron, we have carbon, then nitrogen, 74, and finally the smallest is oxygen. So this is the arrangement of these elements based on their atomic radius. Now you see that the smallest element, as shown here in the configuration, let's put lithium here for convenience. So the smallest element is in fact the biggest. It is because as the element increases and as we go on across the period from left to right, the size becomes smaller because there's an increase in the effective nuclear charge, which is pulling the electrons closer together. But when we talk about going down the group, now when we go down the group, when we talk about, say this is group 1 given here, then the atomic radius does not show the same fashion. In fact, atomic radius increases. Now that simply happens because new shells are being added. So at top in hydrogen we have only 1, in lithium we have 2 shells, in sodium we have 3 shells, in potassium we have 4 shells. So because of the increase in the number of shells, the radius increases in down the group. Let's arrange these elements to make sure to verify what we are saying. So the smallest element we have is lithium. After lithium, the next size is of sodium. Then after sodium, we have potassium. Potassium, we have rubidium, and then cesium. So you see that now here the order is reversed. So down the group, the atomic size increases. There's an increase. The further down an element in the group, the bigger is its size. Whereas lithium, which is on the top, is the smallest. That is because new shells are being added, and because of it, the radius increases. So that is for atomic size. Let's move on to the next trend. And the last and the final trend is metallic and non-metallic character. Now, what determines if something is metallic and non-metallic is its nature. If it is electropositive, which means if it would give away electrons, then it is metallic in nature. If it is electronegative, then it would take electrons to get a stable configuration, then it is non-metallic in nature. So metals, as you see in the periodic classifications, lie on the left-hand side of the period. Sodium, magnesium, calcium, potassium, they all lie on the left-hand side. I'll show you. So you see all these are metals and they all lie on the left-hand side. All the known elements are on the left-hand side. Whereas on the right-hand side, we have the non-metals. So here we have the non-metals. And on this part, we have the metals. Now, somewhere in between, we also have some things which are called as metalloids. So, these like silicon, like germanium. So, these things, they do not show properties of either metals or non-metals. They show both the properties. Because they show both the properties, either properties, they are called as metalloids. So metals lie on the left hand side, whereas non-metals lie on the right hand side. In between, there is a chain of a zigzag structure of metalloids. They exhibit properties of both. They exhibit properties of both metals and non-metals. Examples are silicon, arsenic, boron, germanium, antimony, etc. You need to remember a few examples from the exam point of view, and you need to understand what is the definition of metalloids. Now, what happens to the metallic character when we go left to right on a period or down the group? So, metallic character means the ability to lose electron and become electropositive. The metallic property depends upon how easily an atom can lose an electron. The easier it is to lose an electron, the more metallic an element is. When we go left to right, the metallic character decreases. You've seen this, that when we go left to right, the number of electrons is increasing. And that is why it will be difficult to remove so many electrons from the outermost shell. And that is why metallic character decreases as we go left to right. The tendency to lose electron decreases as effective nuclear charge on the valence electrons increases. So because the nuclear charge is increasing, it will be difficult to remove these electrons from the outermost shell. And it is also because the atomic radius, so the atom also shrinks, and because it shrinks, it is now closer to the nucleus, and that is why it is able to exert more force, because of which it is difficult to remove an electron from the outermost shell. So let's again write the configurations. So when I write these configurations, you see that the atomic number, of course, is increasing, and that is why more force, there's a greater pull on these electrons because of the increased number of protons in the nucleus. And removing one electron from here is relatively easier, but removing two electrons from here is less easy, and so on. It becomes even more difficult as we go from left to right on the period. So because of this, the atomic, when going from left to right, the metallic character always decreases. Now, when we talk about going down the group, the metallic character increases. Now, why does this happen this happens because when we are going down the group, you see that the number of shells is increasing. And that is why the nucleus, which is in the center, becomes farther away from the outermost shell. So the tendency to lose electron increases because the valence electrons are farther from the nucleus. So if you compare the nucleus here, which is much farther, say this is lithium, this is sodium, and this is potassium, for example. So lithium would have 2 electrons. Yeah. So now you see that here, and the gap between the nucleus and the outermost shell is relatively less. Whereas here there's an increased gap in the outermost shell and the nucleus. So because of which it is easy to remove an electron from the outermost shell. So when we talk about all these elements, we see that in fact it is harder to remove an electron when it is closer to the nucleus because there's a greater nuclear pull. But when a new shell is added, the electron becomes farther away from this nucleus, and that is why it is easy to remove it. So when we go down the group, the metallic character increases because it is easier to remove an electron from the outermost shell. Now the non-metallic character, which is electronegativity, would work in the opposite way. Non-metallic character depends on an atom's or an element's ability to gain electrons to become electronegative. So how the more easily it can gain an electron to become electronegative, the more non-metallic it is. Non-metallic property depends upon the ease with which it can gain an electron. So when we go from left to right in a period, as you've seen, the left side is full of metals and the right side is full of non-metals. So even by just observing the trend, you can see that it would increase. So the tendency to gain electrons increases as the effective nuclear charge on the valence electron increases. Now the nuclear pull is increasing, and that is why it can attract a new electron from outside with a better force, and that is why when we move along a period, you see that the non-metallic character increases. So because there is a greater effective nuclear charge, there's a greater force of attraction with the new electron that you want to take, and also because the atom has become smaller, so it can exert the pull better. When we talk about down the group, the non-metallic character decreases because because new shells are being added. The tendency to gain an electron will decrease because the new electron that has to be gained is much farther away from the nucleus as you go down the group, and that is why it is hard to become electronegative. So down the group, it decreases. We can take the example of group 1 with hydrogen, lithium, sodium and potassium. So hydrogen is, the nucleus of hydrogen is still relatively close to the outermost shell, and that is why it can take in an extra electron. But when we go down, now here we have an when we have to take an electron here, the nucleus has become farther away, and as you go on further, you will see it becomes even farther, and so on. So as you go down a group, the outer shell becomes farther from the nucleus, and that is why it cannot exert pull, and there is lesser force of attraction from the nucleus, and that is why the element becomes more and more electronegative on going down the group. This is due to the gradual increase in atomic radius. So as the radius increases, it becomes difficult to take an extra electron. Now the last portion talks about the nature of oxides, which can also be studied based on the periodic classification. So from the modern periodic table, we can predict the nature of oxides. The oxides of metal, which are on the left side of the table, will be basic in nature, whereas oxides of non-metals, which are on the right side, will be acidic in nature. So you can make a lot of inferences based on this classification system, and thus the elements arranged in modern periodic tables show periodicity of the properties like atomic size, valency, metallic, non-metallic character, etc. So all these properties are explained in a clear manner when you study this classification, and it is in fact one of the greatest achievements in the classification with which you can understand elements much better. In this activity, we will understand how the modern periodic table's long form of periodic table is arranged. Note that in 1913, H.G.J. Moseley showed that by X-ray analysis that atomic number is more fundamental property of an element than atomic weight. Therefore, he slightly modified Mendeleev's periodic law and replaced the word atomic weight by atomic number, as was believed before his work was done. It states that physical and chemical properties of all elements are periodic function of their atomic number. This is also the modern periodic law. On the basis of the above law, Moseley prepared a long form periodic table which consisted of 7 periods and 18 groups, as you can see here. The groups are vertical and the periods are horizontal. The subgroup A and B are separate in the table. Now why is that? Now the subgroups are separated in the table and represented at the bottom, as you can see. The transition elements are accommodated in the middle area of the table. So these elements which are popping up are transitional elements. These are called as transition elements, and they occupy the middle portion of the modern periodic table. The strongly metallic elements, which are alkali metals and alkali earth metals, occupy the group 1A and 2A respectively in the left hand side of the transition elements. As you can see here, the red color labeled elements are basic in nature. The non-metallic elements are placed on the right hand side of the transition elements. As you can see here, they are all non-metallic elements, and the previous alkali metals and alkali earth metals were in red, and here they are in mustard green and mustard and green color. The blue elements here are rare gases, noble gases, which are placed in 0 group at the end in the last column. The elements occupying the left and the right wing vertical columns or groups are called as normal representative elements. So these elements are normal representative elements. Now that we have understood this arrangement, we also need to talk about the rare earths, the lanthanides and the actinides, which are called the inner transition elements. They are kept outside the periodic table to mark their peculiar properties. So because they have separate properties, they are kept outside the main structure. The horizontal rows in the periodic table here are called as periods. There are 7 periods in all, and such that each period has consecutive or continuous atomic number. So it goes on increasing. The vertical columns in the periodic table are called as groups, as you can see here. There are 18 groups in the long form periodic table. The element in each group do not have a consecutive atomic number. The elements in the zero group are called rare gases or the noble gases. They are inert and have special property of fully filled outermost shells. So this is our modern periodic table in the long form. It has periods and groups. The arrangement is based on the atomic number, and there are specific groups like the red colored, like there are metals on one side, non-metals on one side. We also have a group for all the zero gases or the noble gases, and actinides and lanthanides are kept separately because of their separate properties.